Hello everyone. In this video, I'm going to talk about dielectric slab waveguide. Uh, in three-dimensional sense, dielectric waveguide is a sandwich of three layers. The middle layers is so-called the core layers, and on the top and bottoms, the core layers is protected by a cladding layers. And for symmetric dielectric slab waveguide, I have to assume that the cutting layer on the tops and the cutting layers at the bottom are the same. And this is today's focus. And the width of the dielectric waveguide is W. The thickness of the core of the dielectric waveguide is 2D, 2 times D. And to begin with, we are going to be based on an assumption that W is much greater than 2D. In the two-dimensional illustration, just suppose your eyes is looking at the other sides of the dielectric waveguide, then you will get the cross-sectional view. The middle layer is the core. The refractive index of the core is n of 1. And the refractive index of the cladding is n2. And I am going to assume that the y-axis is what is coming out of the paper. So the vertical one here is the x-axis, while the horizontal one towards the right direction is the direction of propagation, the z-axis. And in the middle, along the middle line here, this is where x is equal to 0. Since the thickness of the dielectric waveguide is, the thickness of the core is 2D, so the height of the upper boundary is x equal to D. And the height of the lower boundary is x equal to minus D. And because of the assumption that the width is much greater than twice of the D, the value of D, then we can readily assume that there will be no field variations along the y-axis. The field distribution at this point here will be the same as the field distribution at this point here. So this is the so-called low variation of field distribution along the y-axis. So in this case, partial y will be assumed to be 0. So this is a key assumption that make the derivation smooth and successful. Okay, so now we are going to use Maxwell equation to solve the problem. Maxwell equations. So we are going to use curl of E is equal to mu h u t. And remember, the time derivative can be replaced with j omega mu h. And at the same time, the other Maxwell equation is curl of the magnetic field, and is written in this manner. And against the partial T operator can be replaced with J omega and then E. So you have equation 1 and equation 2. Now, to begin with, let's define the wave number, all these things. Now, the wave number, the free space wave number, is K equals to 2 pi F lambda F, yeah, and this is omega, and we can also rewrite this omega. Now, assuming that the dielectric materials are non-magnetic, so assuming non-magnetic material, for the core and the cutting. So we can rewrite K as omega mu naught, and then the relative permittivity, and this one. And we already know that we already know is sorry, n square. N square is epsilon. N square is epsilon. N is the refractive index. So in this case, we can rewrite this as and then, so clearly you can replace this with N, and this is K. So I hope this is clear enough. And in the dielectric waveguide, if you plot the electric field Ex, Ey, if you plot this, so suppose here is x is equal to 0, sorry, suppose here is x equal to 0, and here is x equal to d, and x equal to minus d. And if you plot the profile of the electric field, you will find we have only two distinct modes. One is so-called even mode, where the pattern of the electric field distribution is symmetrical along the middle axis. And this is so-called even mode. The other is anti-symmetric. So it will be like this. It will be like this. So actually it's like this. So in the middle here is 0, and here it will be equal to C, and here it will be equal to D, and here is equal to C, and here is equal to D. So this is the utmost. So the distribution of the electric field uh, uh, along the x-axis, I mean the vertical axis, may be either fully symmetrical or anti-symmetrical. Okay? Now, let's assume that the electric field can be expressed in this manner. And we have shown the direction of propagation is k of is z. So that's why we can have shown the electric field can be written in this manner. So we already have shown that partial y is equal to 0, and as a result, this function can be rewritten as, so it has only one dependency, x. Now, if we calculate partial z for E, then what we will get here is j k z, and then so as a result, we can actually rewrite this in this manner. So both sides of the equation have z, so we can conclude that the partial z can be replaced with this one. Okay. Similarly, we can also continue with this process. We can differentiate this equation one more time with respect to z, and we will get jkz minus j, and then we end up with the same expression. So from here, I can say this is kz square. Yeah, because minus and minus become positive, and minus 3, square root of minus 3 times square root of minus 3 is minus. Okay, so here is e. So as a result, we can conclude that partial z square is equals to minus kz square. So these are the key we need to know in order to simplify the Maxwell equation. Now, to continue, the next thing that we are going to do is to decompose the curl of E, which is equals to minus J omega mu H. So we are going to decompose this equation, the first equation. So if you decompose it, if you do it carefully, you will end up with partial V, partial Y, partial V, and then J omega, and if you continue with this process, you will get this. And this. J omega E of V. I'm sorry, I should say decomposing of H, and this is equal to E. Sorry, I'm making wrong here. So it should be the final mass Maxwell equation. And if you are trying to decompose curve of E is minus H, then what you will get here is partial E Z Y, and then partial Y, and then minus J X, and then partial X. So you have to do it very carefully. It's very easy to make a mistake. And then so we have altogether we get 6 differential equations as a result of the decomposition of the curve equations from the Maxwell equations. So here should be H, and this is epsilon E. So this is what I done. So now what we can do now is to simplify the equation. So now here, see here, this one is obviously 0. So we are going to cancel all the partial Y terms. Here, we cancel. This one, according to what we have learned, can be replaced with minus J, K, Z, and then H of Y. And similarly, this one, we can do the same, minus J, K, Z, H of X. And what else? Here, the same, minus J, K, Z, and then E of Y, and then this one, J, K, Z, E of X. So we are going to, based on these simplifications and we write the Maxwell equation, and we don't need to use solve all 6 equations in one go. We just separate them into TE mode and TM modes. It may not be immediately visible for you which one belongs to TE mode and which one belongs to TM modes. Yeah, for dielectric slab waveguide, we are not going to focus on the solution in the direction of propagations. Instead, we are going to extract the horizontal component E of y or H of y. So what we are going to do now is to focus on E of y. This is the main focus of the equation. And this one, and this one, I cannot explain to you how I know it, but I can say this one will lead to TE mode. And this one will end up with the solution for TM mode. So we are going to focus on this one first. And then we simplify this. So in this equation, we have a few variable. One is h of x, and the other is h of z. And in this one, yeah, I'm right. This one, right? We have this. So we for the time being, let's focus on the TE mode first. In the TE mode, how can I extract h of x? Let's see. We need to find an equation that will, here. We can use this equation to replace it. So this one can go to here. The hx, it can go to here. And h of z, here. We can use this one, and then we can substitute this to here. So this is the key. So this is the two variable. So from here, I can say h of. So I'm going to rewrite the equation. So we have kvx minus and we have this one and we have this one. So let's focus on this one. Now, let's say let's label the equation first. Let's label the equation first. Say this is equation 3, 4, 5, 6, 7, 8. So what we did was we take out 4, 6, 8. 4, 6, 8. So you can see, right? We can eventually substitute to here, and if you do it very carefully, yeah, I can do it for you. I can do it for you. So from 6, you get k, z, and then omega e of y, and this is x. And from a, we get omega mu z. Okay, we substitute h of x and substitute h of z to equation 4. And let's see what we can get. If we do that, then we will get k z e y omega omega. Okay, it's not very clear. Omega and minus h is there, so it's minus j omega mu, and then partial x squared. So this is what we can get, and here we just rewrite it. So this is the rewritten equation of equation 4. Yeah, now let's do some cleaning, right? So eventually, what you end up with here is e of y squared, and then with a little bit of algebraic manipulation, you get omega squared k of z squared e of y. Okay, so now let's do further cleanup for this one. This one is k squared. Yeah, we all know that. And previously we have already worked out this one, so you can continue. So this one is n k naught square. My case is square. And remember, one thing, we already know k square is equal to kx square plus ky square plus kz square. This one, we know it is 0 because there is no variation in the direction, in the y direction. And based on the information here, I can say k of z square is equal to k square minus kz square. So this one is n So this is the what we get. So in other words, the newer equation that we derive, say equation 9, can be written as x, yeah, x, and then minus k x squared. So this is the governing equation, the main governing equation for the solution. So these are the main one. So this is equation 10. And other thing is like this. Now we are going to examine the solution. In the core, we have something like this. So N1 and N2 and 2. The wave can go on. You can undergo the process of internal reflections until it emerges. So in this case, it's a kind of vibrating wave within the core. But in the cutting, we don't expect any wave propagation here. So we expect the wave to die down. So in the core, wave can propagate. The wave can propagate. This means K of x must be real and positive. So this means that in order for K, because K of x, according to this equation here, is equals to Kc squared. So we can conclude that in order for this number to be real, this number has to be bigger than this in order to generate a positive number. The square root of the positive number will give you a real number. And that's why we can conclude that so this is a important criteria, and this criteria can be used for the core. Now in the cutting, the situation will be different. In the cutting, there should not be any wave propagation. In this case, Kx must be an imaginary number. Imaginary number. So this means Kx is not real. Imaginary. So the only condition that will lead you end you up with imaginary number is for Kz bigger than this. So it's the complete opposite. Kz greater than. So this is the condition for the cutting. And I'm going to use these two criteria to come up with the solution, absolute solution. Now, let's take a look in the waveguide. So you have two channel, you have two cutting layer, and the middle. So this is the x-axis. So in the middle is x equal to 0, and here x equal to d, and here x equals to minus d. Or maybe the drawing is too not large enough. I'm going to replace this drawing, too small. So now let's redraw the path in a more clearer manner. So let's say this is the cutting. So this is the x-axis. Here is x equal to 0, and here is x equal to d, and here is x equal to minus d. And we know that inside the core, as it begin, we have n k naught square bigger than kz square. Is it true? Yes, kz square. And this n, because we have shown the refractive index of the core is 1, so n of 1. So we will do this. In the cutting layer, we have the different assumption. K of z is bigger than n2 k naught square, and similarly so these are the assumptions we need to make. So let's deal with the core first. The core have wave, so we can assume the solution to the differential equation. Number 10, this one is a sine kx square plus b cosine kx square. And this will be the solution when x is within this limit. But in the cutting, in the upper cutting, you can rewrite the equation E of y is equals to c, and then alpha. What is alpha? So where alpha is equals to the opposite. So kz square minus n2 into k naught square root. So this is the value of alpha. is opposite to kz. So kz is inverse, and 1 square. Okay. Maybe I need to. So I need to clean up a little bit. This cannot be too messy. So we have this expression, and in the lower cutting, and we can do something similar to this one, but now the x is below minus d. So this way, e of x, we just negative everything. So d. So we don't know the value, right? So d, and then alpha x plus d. So this is a very fair assumption. So say this is equation 11, and this is equation 12, and this is equation 13. Okay, so now we are ready to, unfortunately, the problem is we have only 3 absolute solutions. We have 3 equations, but how many unknowns we have? A, B, C, D, and then alpha, K. Altogether, we have 6 unknowns. You cannot resolve 6 unknowns with only 3 equations. This is where the problem is. So what can we do? First, we can use boundary condition. The boundary condition for this one, the electric field E of y is the tangential electric field. E of y in at x equal to d. So we are going to find E of y in x equal to d, the boundary condition. So boundary conditions. We use the boundary condition to find out as much parameters as we can. So based on this information, if we substitute to here, then we will get a sine k of xd plus b cosine k of xd. And this is going to be e of y, and x is equal to d, and e of y is equal to, again, looking from the size of the cutting, we know that c x minus alpha, and then d minus d. So d minus d is 0. Exponential of a 0 is 1. So it is eventually equal to 1. So this is an important finding for this one. And this had to be equal, yeah? Otherwise, it doesn't make sense at all. So this is the boundary. A sine kxt plus b cosine kxt is equals to c. So this is equation 14. And in the same manner, we can also find the boundary conditions for x equal to minus d. And if you go through the same analysis, we can get minus a sine kxt and then plus b cosine kxt, and then I'm not going to go through all the analysis. I just go straight to the, and then we substitute d here, straight to the equation 13, substitute d here. So obviously we'll get d. So this is what we get. Now, even with the boundary condition for the electric field, at best, we can, there's not much we can do. We can find very little information here. And we end up with 1, 2, 3 unknown, but 2 equations. Actually 4 unknown, including k of x. But we have only 2 equations, so that is not going to be enough. And let's take a look in the magnetic field. So this is what we have just looked at, is electric field. At the boundary condition. Electric field with the boundary condition. I'm looking at the magnetic field. Magnetic field at the boundary. So let's take a look. I don't know whether it's x or xy, right? I just know differentiation. Differentiation will turn the equation into magnetic field expression. So now we do this. So we differentiate this against x. So a cosine kx, and then this one is minus b sine kx. So I'm not going to, so this is one, and if we differentiate this one, then so for the core, and minus alpha c, and then and this is for the upper cutting. So x is greater than d. Okay, I write it down here. Yeah, x is greater than d. And this one, x minus or d. So again, we are going to do the bottom one. Should be the opposite, huh? Minus d. So we are trying to work out the boundary condition for the electric field and also the magnetic field. The magnetic field is always, according to Maxwell equation, it can be found by curl, right? We can just do this and we can get the magnetic field. Now, magnetic field and the boundary should be continuous as well. And given that there is no charge on the surface, then it should be continuous. This means when you consider the upper boundary, should be the same. So at this point, the magnetic field should be the same. So magnetic field when x is equal to d, then according to here, kxd minus b sine kxd, and then here, now if you put x equal to d in this equation, this one will be 0. So as a result, what we get is our c. And again, we can continue with the process. We can continue for the lower boundary. We can do the same. So this is equation 14. 14. Okay. Sorry, this is equation 14, and this is equation 15, and this is equation 16. 16. So 16. Now we are going to develop one more equation similar to this one, but for the lower boundary. And in this case, partial y x, and then x is equal to minus d, and according to here, we will get kx a kx d minus d, and now minus, right, then it will become plus. And this one, if you put minus d here, then it will become r over d. So this is 17. So now, what we are going to do is to extract some equation. Now, first of all, what we can do here is we try to get the sum and difference between these two equations. Now let's do sum first. 14 plus 5. Let's see what we get. We will do a sum of these two equations. Then this got cancelled out. You will get 2b cosine k of xd on the left hand side. On the right hand side, you will receive as d. So we can get 14 plus 15. We get 2b cosine kx c plus d. And we also try to get the minus, and you get a c minus d. So these are very variable equations. You can use it very, very efficiently. So this is 18 and this is 19. And now we can do the same for the last two equations. This one and this one is very difficult to see. Right? I better rewrite this one to the top, cosine minus. So I better write it here. Ey ex is kx a cosine. And then minus b sine k of x d, and according to here, minus alpha c. So this is 16. So now what we can do, we can also do sum and difference between these two equations. So the sum 16 you know that, right? When we sum them together, then this one will become cancel out. So you end up with 2kxa cosine kxd, and then here c plus d alpha c minus d 20, and we get a minus as well. Again, we can do this, right? Or we can, or just the other way around. The other way around, either way you would do. So 2 or 2b 9 kx d and c plus d. So c plus d. So c plus d. And apparently this is a plus sign. Okay, now, so this is 21. So everything will be in order. All we need to do is to do some extract and remove. And this one, we have a cosine term here, b cosine. So this one is for even mode. Even mode. This one, the odd mode. We know that because in even mode we have only cosine term. In odd modes we have only sine terms. So we can rest assured that for exactly the same reason, this one is even mode and this one is odd mode. So what we can do is we can separate the even mode and odd mode and then find the solution. we can now let's take a look here. Even and odd. Now let's combine the even mode and odd mode. So now what I'm going to do is to do equation 18 and equation 21. We have got this equation. So what we can do here, either way we'll do it. So 18 divided by 21, and let's see what we can do. So 18 divided by 21, so it's cotangent k of x. By the way, I miss out the k of x here. Okay, k of x d, so 1 over k of x is equal to the same, so 1 over alpha. So based on the information here, I can find out. Sorry, this one should be even. This one should be even. This one should be odd. So because we have a here, so odd and even. Yeah, the magnetic field is not the same as electric field. So we got this equation. Now we just do a little bit of manipulation. Alpha move to the left, and kx move to the right, and cotangent move to the right. So this is the number one characteristic solution for the symmetric dielectric waveguide. So 22, it is an important one. Now let's take a look in the other two equations. Again, right, we combine the odd equation. Yeah. So 19 divided by 20. Let's see what we can get. So 1 over kx tangent kxd, and then minus alpha. So as a result, from this equation, we get minus alpha is equal to kx cotan, and then k of x d. So we have got two important characteristic equations, which will end up with the major solution. So I'm going to be right here. Yeah, let's write one more equation. The other equation is kx squared plus alpha squared. And let's see what we can do. Kx is equal to n1 k0 squared minus kz squared, and this one kz squared minus n2 So if you do this, this one cancel out. So k log square n1 square minus n2 square. So this is the number 3 characteristic equation. So I'm going to rewrite here. Yeah. These are the 3 solution equation. And you will, with this, you'll be able to resolve the characteristic of the dielectric waveguide. So first of all, let's do some attachment. This one here, we multiply both sides of the equation by d. So multiplying by d. Then this will become d k x d, and then kxd. So now the argument for tangent is the same as the coefficient, and this is the number 1 important thing. It's 23, and we are going to do the same for equation 21 by d. And for this one, we are also trying to do it. In this case, we multiply d square for 22 by d square. So what we can get here is x d square over d square, and then k naught square, and then n1 square and 2 square. Now, there is a name for this variable. This variable is so-called the V number square, where V is k naught d, and then square root of n1 square minus n2 square. And this is the important characteristic equation. Fine. So we have got 3 important characteristic equations. And what we can do here, we can assume k of x times d is the variable for the horizontal axis. We can assume alpha d as the variable for the y-axis. And equivalently, this is actually the equation. Equation 25 is a circle. So let's check how it works. So if you plot the vertical axis as alpha d and the horizontal axis alpha k of x d, then according to equation 25. Sorry, D. Is equal to V square, where V is equal to N K naught N1 square minus N2 square times K naught D, KXD. So it is a circle. So if this is the case, I can draw a circle into the board. So assuming that the radius here is V. So this is the circle. And representing this equation. So now how about the tangent? Tangent, so the other equation is what D is equal to KXD tangent KXD. And I'm going to rewrite this one here. So what we need to do is to use this graph to solve the solution that satisfies all three equations. So if I do this for this one, I will end up with some pattern like this. Here, it will be infinitive. So what does it mean? Yeah, the value of tangent becomes infinitive. This means k of x d, k of x times d is a multiple of half pi. Say, for example, in this case, 90 degrees. So pi over 2. And how about here? K of x becomes 0. Then you will end up with infinity, or pi, 2 pi. 2 pi. So here, or equal to pi, sorry. So this is the second one. So pi. So this comes from KXD cotan KXD. So this one. So if you continue with this process, because K of XD have more than one solution, so we will do this. You get the same. So this process can continue. So before doing anything, I want to ask you to pay attention to the value of KXD. So do you agree that there is a crossing in this graph? And this crossing represents the point which satisfies all three equations. So the coordinate here will be kx d. Yeah, for example, this is 0, and this is 1, and this is 2. So kx 0, and then alpha d 0. I can say, and this one is kx 1, and then alpha 1 d. So I can do that. So based on the information, yeah, before doing anything, in the core, we know, yeah, we just go back to what we have derived. In the core, we know that k squared is greater than kz squared. So kx must be real. And this is the condition k naught squared greater than kv squared. And in order for the internal refractions to be successful, we have to ensure N1 is greater than N2. This is the case for all the dielectric waveguide. Otherwise, there will be low internal refraction. So N1, N2, N2. So this is so-called internal refraction. And to be able to have this situation, you have to guarantee N1 greater than N2. So this means V is real. So the only thing that would allow us to have this situation is for the point inside the circle. Outside the circle, you won't get this. Inside the circle, then you will get this. Inside the circle, you will get N1 square larger than N2 square. Another point is the crossing. The crossing represents where alpha becomes 0. And if you take a look in this equation, we have kx d square plus alpha d square, and then we have v square, so kx d, and then n1 and 2 square. So from here, we can say if we remove d from both sides of the equation, let me see. I think here is no, yeah. It cannot be 0, yeah, no. So this is no. So alpha is equals to k log square n1 and 2 square minus kx square and square root. So this is the equation, the so-called characteristic equation 15, 25. We'll get this. So this is a value of alpha. So in this case, first we need to determine the value of kx when alpha is 0. So when alpha is 0, according to this one, according to this axis, k of x d is equals to the multiple of half pi. The multiple of half pi may be written as m pi over 2. If you don't want the value to be 0, then that's fine, right? But here, m can be 0, 1, 2, until infinity. So in this case, k of x is equal to m pi over 2d. And let's say this is equation 26. And from equation 26, we can substitute this value into here. And substitute alpha is 0. And if we do that, then we will get this. M pi 2d square. Now, the only way for this value to be 0 is for both terms inside the square root to be the same. So m pi over d square 2d square is equal to k naught square n1. Or you will just do the square root n1 square and 2 square, and then m pi over 2d. Now, when alpha is 0, the frequency is the so-called cutoff. I can say, why we can do this. The frequency here is V and omega and remember this V is the velocity c, because this is k naught, so this is c, precisely this is c, so we can say this. And by the way, n1 square is one square relative epsilon. There is no such thing, no square. And allow 2. This one is the relative permittivity for the cutting. This one is the relative permittivity for the core. So I replace the refractive index with its relative permittivity. So as a result, you can say omega, and here and of course you can write this omega So if you want to know the omega for this condition, then you will get m pi 2d. So this is the frequency at which alpha is 0. The frequency at which alpha is 0 means the frequency at which there is no more gradient. You know, alpha, when alpha is 0, there's no more absorption. In this case, the wave will leak. So in optical domain, the cutoff frequency represents the frequency where there is no more wave guiding. No more wave guiding is the condition where alpha is equal to 0. So you can say this is the cutoff frequency. And m here can be 0, 1. M is the mode number. Sorry, I cannot see. Yeah, I have to move the page a little bit up. Sorry. So this is what we can get. Okay? So this is the cutoff frequency for the electric field, and we have already got the solution for Kx. Kx can be found directly by reading off the x-coordinate of this point. And if you know Kx, then you know the solution, E of y. And how are we going to find the magnetic field? So if you go back to what we have learned when we derive the Maxwell equation, the E of y, yeah, here we go. The E of y represents, I'm going to copy this equation. E of y can end you up with h of z. The equation is 3 omega. So to find the magnetic field in the direction of propagation, we use this equation. So according to here, so we just need to do that. Depending on what mode you are talking about, all modes or even mode, you just need to substitute this into this equation and always use this equation at the core to do that. So if you do that, then you will end up with A sine kx plus B cosine kxx. So this is what you are going to get. previously we have already managed to find kx, and you can substitute kx here, and then this is your solution. And if you have any question, please feel free to leave your question to the comment section of this video. And in the next chapter, we will focus on TM mode. This is the solution for TE mode. Okay?